Okay, great. Thank you very much. So I'm going to be switching length scales, which is a good reminder that I often in my talks speak about doing large scale simulations. And it's an important reminder that actually what you mean by a large system depends very much on the method that we're using. But so I'm talking about density functional theory, and so by large systems in this context, I mean the thousands to tens of thousands of atoms or so regime. So just to give a quick outline, so first of all, I'm going to talk about why we're actually interested in simulating thousands of atoms using DFT. And then I'm going to give a quick introduction to the use of DFT with a wavelet basis set in the BigDFT code that I developed. Then I'm going to talk about how we can implement a linear scaling approach in the BigDFT code, how we can then further kind of reduce the computational cost by dividing our system into fragments and exploiting that. And then how we can somehow reduce the complexity of our simulations of large systems and try and extract new types of information. And then I'll just finish with a summary. So why do we actually need to do quantum mechanics approaches such as density functional theory for systems containing thousands of atoms? So on the one hand, we have a DFT, which has been very successful at the sort of tens to hundreds of atoms or so regime. And on the other hand, we have our classical molecular mechanics approaches at the kind of tens of thousands of atoms plus regime. And of course, we also have the possibility of doing QM-MM approaches, which already combine the two. But one thing we'd like to do with large-scale DFT is to bridge the gap between these traditional regimes of QM and MM. One of the reasons for doing so might be to try and validate our approaches that we use at large scale by being able to do a purely QM approach at such system sizes. We also, if we're doing QM-MM, for example, we might want to be able to have a larger QM region. And so for that reason, we need to be able to treat a larger system. We're sometimes also interested in calculating intrinsically quantum mechanical quantities. So one thing I'm interested in, for example, is electronic excitations. And we also might want to just simulate materials which are complex. So whether that's something biological, as I'll be giving a few examples, or whether that's trying to encapsulate more realism in our materials. So for example, if there's long range disorder or some kind of extended defects that we want to capture. But also once we get to DFT for such large systems, in some ways, this also implies new ways of working and new ways of capturing information. So it's not as easy if you have thousands of atoms to kind of look at your system in detail and understand what's going on. So in some ways, we want to try and capture information differently to what we would do at a small scale. So this is just a figure that we had in a recent review paper, both of which references are here, where we tried to answer these questions of both why do we need QM of such large systems and what can we do when we have it. So one of the things I'm going to talk about is trying to extract information by dividing some complex system into fragments. So whether these are amino acids or some other kind of fragment, and how can we quantify and analyze the interactions between these fragments. So I work with a code I mentioned called BigDFT. So a lot of DFT codes in the chemistry sphere tend to work with a Gaussian basis set, and in the physics sphere tend to work with a plane wave basis set for periodic systems. And in some ways, wavelets bring together the advantages of both of these two families of basis sets. So there are a number of different wavelet families, and they all have different properties. But we can have wavelets which are localized in both real and Fourier space. We can choose to have an orthogonal basis set of wavelets, and they're also systematic. So they have the same advantage of plane waves that you can systematically converge the basis set to get to the complete basis set accuracy limit. We also can have, analytic operators. And then finally, we have kind of a special property that's known as adaptivity or multi-resolution, just to show what this looks like, taking the simplest possible family of wavelets, which are called Haar wavelets. We have this RID functions, which are called scaling functions. So by combining two scaling functions at a finer resolution level, we can go between two different resolution levels. But we can also combine these scaling functions with the blue function that we call wavelets. So by combining different regimes of scaling function and wavelets, we can have different levels of resolution while still having a fixed grid spacing. So this allows for quite an efficient basis set approach. So as I mentioned, there are lots of different families of wavelets. So in BigDFT, we use the least asymmetric Dolbesch's wavelets of order 16, which is a bit of a mouthful, but they look like this. So the red function is the scaling function and the blue function is the wavelet. So in BigDFT, we choose to have just 2 resolution levels. So we have what we call the coarse grid, which fills our whole simulation space. And then we also have a fine grid, which is twice the resolution. And this is the region nearer the atoms where we expect the wave functions to be varying more strongly. So also in BigDFT, we can do a range of boundary conditions. So we can treat molecules, wires, surfaces, and also solids, but only in orthorhombic boundary conditions. And we also have recently been working on a Python-based PyBigDFT interface for Jupyter Notebook workflows to make life a bit easier for joining together more complicated types of simulations. And it also is an open source code, just in case anyone is interested, you can freely use it. So once we combine these favorable properties of wavelets with the power of high performance computing, we can normally simulate up to about 1,000 or so atoms, but we still suffer from the cubic scaling limitation with the number of atoms that is common to many DFT codes. And not just in terms of computational cost, but the scaling is also cubic in terms of memory, which often tends to be a more important limitation. On the other hand, it's been known for quite some time that the behavior of large systems is short-ranged or nearsighted. And more specifically, the density matrix decays exponentially in systems with a gap. So the question is, how can we exploit nearsightedness to treat large systems? So there are a number of different ways of doing this. So we choose to use an approach which relies on rewriting our extended cone-Shor tools, which are allowed to delocalize across the whole system in terms of some localized functions, which we call support functions. So the cone-sham orbitals just become a linear combination of these localized support functions. So this is the approach that's also used, for example, in the one-step code. So then once we have these localized support functions, we can rewrite the density matrix in terms of, instead of the cone-sham wave functions, the support functions, and a quantity known as the density kernel. So since we no longer have any explicit reference to the cone-sham orbitals, we also want to avoid diagonalization to get rid of this cubic scaling. And then we can express both the density from the density matrix, and also we have some matrix expressions to get the total energy or the number of electrons in the system by taking the trace of this density kernel with either the overlap matrix or the Hamiltonian matrix. So just to say a bit more about these support functions, so these are strictly localized within some radius, usually around 6 to 8 Bohr, but this is a user-defined parameter. So just like the underlying wavelet basis, you can systematically converge the calculation by increasing this radius. We usually have a minimal basis, although the user is also free to choose this. So usually one support function per hydrogen atom, 4 per carbon, nitrogen, oxygen atom, etc. These are also atom-centered and quasi-orthogonal. And these are fully numerical functions which are expanded in a wavelet basis set. So they live on a grid still, but in strict localization regions, which are these spheres I show here. But we still inherit the coarse and the fine grid of the cubic scaling BigDFT code. And also for linear scaling BigDFT with the support function approach, we work at the gamma point only, so we can have real support functions. So we start with an atomic orbital guess for the support functions. As I mentioned, these are numerical functions. So we start by expressing atomic orbitals in the wavelet basis set. And then we impose a confining potential. So this quartic confining potential that we add to the Hamiltonian. And then we optimize the support functions by minimizing the total energy with respect to their numerical form. So what this looks like, just as an example for this particular molecule. So we have some S-like support functions and some P-like support functions. But if you look closely, you can see that the S-like orbitals, for example, are no longer really spherical. And the P-like ones have also distorted slightly. So these are kind of adapting to their local chemical environment in such a way as to minimize the energy. And if you kind of project or average out onto 1D, you can see that the difference between the dashed line, which is the linear combination of atomic orbitals guess, and the final optimized support function is actually relatively subtle. But this makes a big difference in the energy, in that we have quite a small error once we've optimized them with respect to using the full delocalized wave functions as we do in the cubic scaling approach. So by combining this support function optimization with this representation on the wavelet grid, we end up with a minimal localized basis set, which has the high accuracy of wavelets. So then we need to put all these ingredients together into an algorithm. So we minimize the energy with respect to both the support functions and also the density kernel. We have a few different approaches for optimizing the kernel, but we usually use the Fermi operator expansion as our true linear scaling approach. And then we repeatedly optimize both of these until it's converged. And then at the end, we can have our total energy as well as our forces. And I said we wanted to avoid diagonalization, but if we do want the cone-sham energies for some reason, we can do a one-off diagonalization at the end for relatively low cost. So if you put this algorithm together, we've also, as I mentioned, imposed strict localization, and this leads us to sparse matrices, especially as we truncate the density kernel. But this sparsity depends on both the size of the system, but also other factors like the dimensionality and the choice of support function radii. And all of these factors influence the point at which you have a crossover between the linear scaling and cubic scaling calculations. So how many atoms do you need to go to before linear scaling becomes favorable compared to cubic scaling? So here I've just shown an example of a quasi 1D graphene nanoribbon versus a fully 2D graphene sheet. So you can see in the one-dimensional system, the density kernel is much more sparse than in the 2D system. And this corresponds to having a crossover point that's a few hundred atoms for the 1D system versus about 1,000 atoms for the 2D system. But as you can see, instead of the cubic scaling behavior, we now have linear scaling behavior, in both in terms of the wall time and in terms of the memory we're using, which enables us to go to bigger systems. So this is already great, but ideally we'd actually like to bring down the cost even more. And so one of the things which dominates the prefactor of these calculations is the need to do support function optimization. But as I mentioned, the support functions adapt to their chemical environment. So this implies that similar chemical environments have similar support functions. And actually, if you would look at the support functions for this little droplet of water, at least as far as the eye can tell, they look very similar. So the question is, could we somehow make use of this fact and reuse the support functions between calculations to reduce the computational cost? So one of the ingredients we need to be able to do to achieve that is to be able to account for varying orientations and positions in a system. So for example, in the water droplet, we've got water molecules at lots of different angles. So what we do is we minimize this cost function, which gives us a rotation matrix between some set of template coordinates and some final system coordinates. If it's a purely rigid transformation, then this cost function J gives us a value of 0. If there's some kind of distortions in whatever it is that we're rotating, then we end up with a non-zero value. But once we've used this to find the appropriate rotation to apply, we then have a wavelet interpolation scheme, which will actually perform this rototranslation of the support functions. So once we have this, we can define what we call a molecular fragment approach. So continuing with the water droplet example, we can take a single water molecule, optimize the support functions, which is low cost because it's such a small system. And then we simply replicate them using this rototranslation procedure for our full system of interest. And then we can perform this large calculation with a fixed support function. So that means we can completely eliminate this loop from our algorithm. So that makes quite a big difference to the cost, but obviously this is only going to work in certain types of systems. So just to show a system where it works really well, one of the applications I'm interested in is simulating materials for organic LEDs. So here we have a cluster of CBP, which is a typical OLED host material. And we show that the cubic scaling, the linear scaling, and the fragment cost, and you can see that for about 5,000 atoms, it ends up being about 7 times cheaper to use the fragment approach than the full linear scaling approach. So it's, in terms of cost, it's working really quite well. We can also compare the occupied density of states between the 3 methods, and this also, the fragment approach reproduces the density of states very well. And the error introduced in the total energy is also quite small. So the reason why it works well in this system is because we have relatively weakly interacting fragments, which are not too distorted. And we can use this cost function J that I mentioned to tell us whether the distortion is too high, in which case we shouldn't use the fragment approach, or whether it's small enough that the fragment approach is going to work well. So just to give another example of an application, so taking this CBP as a host and introducing 8% of guest molecules, which is this iridium PPY3, a typical OLED guest emitter. And so we perform template calculations for each of the 2 molecules. We can then calculate both the transfer integrals using this expression and the on-site energies using constrained DFT to confine a charge to the molecule of interest. And what we found is that for the transfer integrals, the disorder in this system gives us a dispersion in results for both the transfer intervals and the on-site energies, whereas the introduction of the environment using constrained DFT to get the net polarization gives us a shift in the average values as well. So we're influenced not by just the dispersion, but also by the environmental effects. So we also can go beyond molecules. So instead of in the molecular case where we perform a template calculation for a molecule and then replicate the molecules, we also, for example, could perform a template calculation for a molecule and then replicate only the central fragments and use it to perform a calculation on a polymer. So any system where you have some kind of repetition, whether this is isolated molecules or whether it's a 1D system like nanotubes or 2D systems like graphene, we can make use of this fragment approach to save computational cost. And we also can define indicators which help tell us whether it's appropriate to use this fragment-based method. So as well as the cost function J, we can also use what we call the on-site overlap matrix, which basically tells us the similarity between support functions. So in this case, how similar are support functions as you get further away from a silicon substitutional defect in graphene. And this correlates with the error that we introduce. So we have some tools available which help us to determine whether or not the fragment approach is a good approach to use for a given system. So just to summarize the different methods we have available, so we can go from cubic scaling to linear scaling to fragment scaling, each time introducing an additional approximation. We also have an implicit solvent method available that we can combine with both linear scaling and cubic scaling DFT. And we also can go between the methods. So we could use the fragment approach to generate a gas for linear scaling. We could use linear scaling to generate a gas for cubic scaling. So all of these methods allow us to be able to treat systems containing thousands of atoms. But I also mentioned at the beginning that we want to do new kinds of analysis. So how do we actually do that? So the support functions as localized quantities are useful for not just reducing the cost. So they're atom-centered, which gives us a map for looking at atom-based quantities. So whether that's something like the projected density of states, I'm just showing an example of bulk tungsten here, where we compared the weighted projected density of states with X-ray photoelectron spectroscopy measurements, and it worked very well. We can also calculate things like atomic charges and higher order multiples, but can we extract things that people don't traditionally extract from DFT simulations? And the answer is yes. So if we have our density matrix expressed in a localized basis, then we can also define some additional indicators. So this includes both what we call a purity indicator, which enables us to identify pure or separable fragments, which is useful in cases where you don't just have a simple cluster of molecules where it's obvious what constitutes a fragment. We also have a fragment bond order, which enables us to quantify interactions between these fragments. But this fragmentation and these two parameters depend on the basis set, and they really rely on having a localized minimal basis set. So just to give you a couple of examples of how we can do this before I finish. So here we have 11 base pairs of DNA, which we put in explicit solution of sodium and water. So we did the full DFT, linear scaling DFT calculation for this 15,000 odd atom system in a couple of hours. And then we can use this purity indicator to identify separable fragments. So in this case, one of the reasons why it's useful is we first of all calculated the charges on the atoms in the system using a Millikan-based approach. And we find that apart from the sodium, nothing else is really pure. So we define kind of less than 0.05 as a pure fragment. All of the other atoms in the system are not pure. And one of the consequences is also that some of the charges on various atoms are actually unphysical and not what we'd really expect at all. But if we use this purity indicator and look instead at kind of more reasonable fragments, so water molecules and nucleotides, we find that both the fragments are pure where the atoms weren't, and the resulting charges are far more reasonable. So this gives us an unbiased way of identifying separable fragments out of a system. So also another biological system where we can't simply take amino acids or nucleotides. So in this case, the Laccase enzyme, it has these copper atoms, which it's not clear how to join those to a particular fragment. So again, we use the purity indicator to identify some fragments. So this yellow region is our fragment of interest that contains the active site. And then we also use this fragment bond order to define an embedding region. So this is the blue atoms. And by also combining these things, we were able to generate kind of a graph network showing the interactions between the different fragments. And this gives us a coarse-grained view of the system. I've also not shown it here, but Laccase is an enzyme which is used to detoxify the aflatoxin. And so we were also able to look at how these interactions between the aflatoxin molecule and the Laccase enzyme affect how well it's able to detoxify a particular flavor of aflatoxin. And you could also use this kind of approach in future to automate the setup of active and embedding regions for QMMM without having to really know anything about the system, because you can just set a threshold value for both the purity indicator and the fragment bond order. So just the final example, so just in the last week or so, we were able to converge the largest system we've done so far with linear scaling BigDFT. And this is the spike, COVID spike protein. So this is about 52,000 atoms. So we did the calculation also in implicit solvent. In total, took about 6 hours on 128 nodes of Iran, the supercomputer in France. And here I'm just showing a 3D graph view. So we have the three different chains of the spike, which are shown in the different colors. And as before, we're also able to map the interactions between the chains. So the circles show the nodes where there's an interaction across chains, and the color defines the strength of this fragment bond interaction. So we're really able to look at systems containing several tens of thousands of atoms and do these sorts of analysis. So just to summarize, so I've shown you how we can exploit both locality and where applicable repetition in different systems to enable calculations of more than 10,000 atoms. And while doing so, we can also have the advantages of BigDFT, that we can have a range of boundary conditions, whether that's 3 boundary conditions, 1D, 2D, or 3D. We can also further exploit the support function locality to reduce the complexity of large systems and be able to understand fragmentation and interactions in large systems. And then 2 of the key application areas that I've showed are both looking at biological systems, so the Laccase and the COVID, and then also looking at OLEDs, where we can understand the effects of disorder and environment. And we've also been developing recently a new method called transition-based constrained DFT for looking at excitations in these OLED systems. And so just to finish with the acknowledgements, obviously there's a number of people behind the BigDFT code. So I've just put our reference paper from a couple of years ago. So particularly William Dawson at Riken, Stefan Moore in Barcelona, and Luigi Genovese in France have been involved in various aspects of the linear scaling and the complexity reduction and some of the biological applications. And thank you for your attention.